Hello, everybody. My name's Professor Richard Sinnott. I'm the Director of E-Research at the University of Melbourne, and I am a Professor of Applied Computing Systems. I work in many different disciplines, many different domains. I've been supporting research-oriented IT for the last 20 years or so. And today in the talk, I'm going to describe some of the lessons learned in building data sharing systems with specific focus on e-health collaborations. On the next slide, my team is fairly extensive. I'm not your typical academic, I guess you could say. So I have a large team of software engineers, and we work on all kinds of applied projects. We have grants from the likes of DARPA, so the defense in the US, and IARPA, who fund US intelligence-related activities, lots of defense work, European projects, et cetera, et cetera. So there's a lot of people who are collaborating with us and funding us to do what we do. I supervise lots and lots of master's dissertations as well, so I have access to lots of students. I teach cloud computing and high-performance computing, but all of my grants generally, or the vast majority, are about dealing with data. So this is the typical big data, heterogeneous data, high-velocity data, very heterogeneous data, which is all across many different disciplines, from arts and humanities to zoology. And a lot of this ties into security. So most of the work I do is dealing with sensitive data, as you can imagine from some of the funders that I'm involved in. On the next slide, I will talk a little bit now about the kind of lessons learned in supporting researchers in the clinical domain, so biomedical clinical domain. They all have different needs and demands. So generally speaking, there's a range of activities I'm involved in supporting collaborations in the sort of clinical domain. A lot of the time, the data is locked in hospitals or in GP practices, and it's hidden behind a firewall. And one of the real challenges is how do you allow access to those kind of data sets, which allow hospitals to share data with each other or with researchers, etc. That in turn has lots of implications on data management. I mean, there is no one solution. There are many, many solutions. There are different databases. There are different data artifacts. There are different sort of systems and applications. And all of that, generally speaking, has an implication on security. So I mean, what the classic sort of adage is, you don't get fired by not giving away data. So most of the organizations I work with are risk averse. In dealing with a lot of this data, that can have implications on high performance computing and visualization, but this tends to be less of a challenge. I mean, I work across the sort of research spectrum in the biomedical domain, from whole genomes being processed, looking at specific diseases, etc. But for the most part, most of the researchers I work with are very much around the clinical side and treating patient side. And before you even get to building those kind of systems, there's a whole range of paperwork and trust and documentation which needs to happen, like ethics and ethics approval. But what data are you collecting? Why are you collecting it? How will it be managed? Who will access it? Whose job is it if this data is somehow, if your systems are hacked, et cetera, et cetera. So there's lots of documentation which is required, and proof and evidence that you're doing the right things with the data for the right reasons. So it's not just about technology, I guess. It's also about the process of applying the technology and for the reasons that you're applying it. On the next slide, I'll talk a little bit about the kind of core tasks which I'm typically asked to support are largely around supporting authorization, I guess you can say. So we have authentication, proving your identity, but then there's a whole issue of who can see and do what with what data. Ultimately, all sites, all hospitals, all practices are independent, autonomous. They decide for themselves what is allowed and not allowed, or they can delegate that to me, in which case I build a database, which I'll talk about in a little while, and I manage the access and the rules for how to access the data. There are a range of technologies in that space which work. And so, I mean, a classic one might be, say, role-based access control, which is a classic. Roles have, if you have a certain role or a certain set of privileges, if you're a doctor or a nurse or a researcher, you might have access to certain types of data for certain reasons at certain times. But there are many different technical solutions to realizing that. And one of the challenges and one of the lessons learned is that most of the practices and hospitals and organizations I've worked with are not very good at doing this. They don't really understand it. They don't have a well defined set of technologies that they trust and roll out for providing that access to their data. So how do I solve these problems? Well, one of the ways I solve those kind of problems is through the architectural definition. How do you design a system where you don't completely depend upon a piece of technology to make a decision for you? And there are different ways in that this can be applied. The simplest one, which is the one I have a lot of experience working with, is where I build a database, let's say a disease registry, where a doctor or a clinician at a hospital will log in to this system and create a patient and create information about the patient. But this data does not connect directly to his local IT systems within the hospital. So I regard that one as an independent, centralized sort of data sharing model. They're creating information about patients, which is now being used and aggregated to understand, if 100 different doctors are logging in, creating information, they can see broader pictures of what's happening in the medical space around those patients with those conditions. That's the simplest one to realize. There are many others. So another one, which is that might work for some conditions, especially rare diseases where there's not so many patients. But sometimes you're dealing with conditions which are a lot more common. So diabetes, which I'll talk about, where you're not going to have someone logging into a separate system. They've already got this data locally. It's captured as part of their daily business. So what we want is a system which that data can be pushed out to a central resource where it can then be analyzed and compared with everybody else's data that's being pushed out. So that's another common model, and I've worked extensively in those domains. That could be because there's too many patients, or you're dealing with real-time data. For example, like say the Avert IT project looked at patients who had a brain trauma. And so we wanted real-time information from the ICU to be able to tell them, to predict when a patient might have an adverse event like the low blood pressure, etc. Another model, which is probably not so relevant for clinical, but it's very common generally, is, if you like, the Federated Open Data Querying Challenge. So you've got all these databases scattered around the internet, and you want to directly access them and query them, and then pull this information back and connect it with other data. So if you can have live programmatic access through APIs or services or service-oriented architectures, that's a very common model also. I have quite a few projects I've worked on in that domain. Sometimes you need to be a bit more creative in how you do things. So I've worked with organizations that were willing to collaborate, but they wouldn't open their firewall for incoming connections from the internet, irrespective of the technology that was used. So they were very risk averse. I'll talk a little bit about how you can design systems that do solve that one, where there's no ingress to the system saying, I want to query your database. Rather, they're pulling in a query, running the query, doing some analysis, and then pushing it out. And this is a completely automated process. It's not like someone has to manually check the data or manually check the query. We've implemented a range of these pull-based data sharing models as well. And then finally is the holy grail, which is I want to be able to query multiple different databases, have all my queries intercepted, check the privileges, check the access, what data is being accessed by whom, etc., etc. And then if I pass all of the sort of authorization rules that are in place, then the data is released and then used for different purposes. I'll talk about that one at the end of the slides. So on the next slide, this is an example of a very basic centralized data sharing model. So in this case, what you'll see you have a hospital, let's say call it site 1. A doctor there will create information about a patient. It might be fully identifying, completely de-identified. It might include, a very basic information like the date of birth, the date of diagnosis for their condition, things of the gender, etc. Or it could be much more involved to create a patient. You could have, for example, how are they being treated? Did they have chemotherapy or radiotherapy? Have they had surgery? What was the outcome of the surgery? Have they got biosamples available? If so, have these been used for particular scenarios? But the point is, this hospital is not having to, I'm not pulling the data out of the hospital. It's a clinician who's entering this data manually into a separate system. In doing that, there are various rules about who can access that data. So the data is being stored in a back-end database, for argument's sake. There is a case of it might be only people from France could access that data if that was a French hospital, if it was from Paris, or it might be only European countries can access this, or only a certain researchers can access it for whatever reason. And so that's a very common model. So a separate independent database, which are people would log into to do stuff, I guess. And the stuff they're doing is largely depend on what that community want. And so there is no unified standard here. I know people have looked at ontologies and people have looked at HL7 and SNOMED and all these kind of systems. At the coalface of what happens in hospitals, it's completely different. So French hospital systems, or even just within Australia, every hospital has its own infrastructure, its own technologies, its own typically legacy data, which they've been collecting over time, and they are, but my role is typically to integrate all of these separate data sets and align them with some common, what you might call a data dictionary. So this is the data that these researchers have identified they want to collect. One example, and one of the more successful examples of this model on the next slide is related to one of the European projects I'm involved in, which is called NSAT Cancer. This actually project finished 6 years ago now, or 5 years ago. And it's a classic example of this data sharing model. So it's to do with certain types of cancer of your adrenal glands. So your adrenal glands are just right next to your kidneys, and they release hormones which regulate your body. So they release, say, for example, adrenaline. There are people who, if you are unfortunate enough to get one of these cancer types, then the prognosis, generally speaking, is not very good. You have no idea you've got one of these cancer types until it's spread through your body. So, and some of them are very aggressive. And so adrenocortical carcinoma, for example, is very rare, but if you're unfortunate to get one, then the chances are you're not going to survive, or you have a very poor prognosis. What the doctors generally want to do is get all the patients that have had these sort of different types of cancers, and then understand what treatments do they get, what's the most effective treatment, which drug seems to work better than other drugs. And so this was what we were tasked to do with for the NSAT project. And when I started this work in 2011, we built a very quick prototype to demonstrate 4 different databases, each one for a particular tumor type. There was imaging, because a lot of the time the patients are having MRI scans or CT scans. They're having tissues or plasma or blood removed and put in fridges, which all have to be tracked. And so a researcher might say, I need access to some of that tissue sample because I'm looking at a study where we're looking at genetic mutations of that particular, or identifying biomarkers for that cancer, etc. So, and all of this has to be seamless and support the needs of the community. So it's about collaboration. It's no use building a wonderful system if no one's using it. You have to be listening to what they like, what they don't like, and evolving the system based on what their needs actually are. Just to give you a bit of results from the data from that system. So I mentioned that these are very rare. So ACCs, adrenocortical carcinoma, there is maybe 1.3, I think it is, per million people might get one of those. So we have over 4,000 patients with ACCs, and we have almost 20,000 patients, or 19,000 in total in the system, which doesn't sound like a huge lot. I guess at the end of the day, it sounds like, well, less than 20,000 patients. What can you learn from this? They can learn an awful lot. I mean, your typical large-scale hospital will maybe see half a dozen of these patients per year, and they are, the management of these types of cancer are woefully not really understood. The actual biospecimens, the blood, the tissues, the plasma, we have lots of information, 33,000 tissue samples existing right now in various laboratories around the world. And probably another key part is the clinical annotations themselves. So anytime a patient has a drug, a chemotherapy, a radiotherapy, etc., or surgery, that's one data point. So we have a very rich data model now on thousands of patients who've had all kinds of cocktails of treatments to identify, or manage them and give them sort of recommendations for how to or what's the best recipe for treating that particular patient, as an older woman, a younger man, etc., with different types of cancers at various stages. As of this last month, there's 112 hospitals around the world using this system, and they are as far apart as South America, North America, Russia, all over Europe, Australasia. So it's kind of galvanized the global community. So that's the registry. And so I mentioned that you might be able to use this for things. One of the key things that people want is to support clinical trials. So finding the 5,000 patients that have got or 1,000 patients that have got an ACC because you want to test out some new therapy is a classic example. So we have many, many clinical trials running as a result of this. So one example of one clinical trial is looking at, it's called a PMT study, which required several thousand patients to be recruited. There's lots and lots of data on the next animation. There's lots of data being collected on those individuals. So, and it's a full 4-phase clinical trial. So it's not just a phase 1 trial or a phase 2 trial. It's actually from recruitment to assessment through to follow-up, et cetera, et cetera. So it's the full cycle. And you see the sort of why the power of numbers applies here. So we start off with several thousand patients coming into the system. A lot of those get ruled out because due to screening, various points, and they'll have certain treatments that are given, and they're looking at the effects of those treatments. Each patient can have over 10,000 data points for one patient in this study. So it's a very, very rich data set of thousands and thousands of patients. And lots of that data can go back into the registry as well. So for example, if a patient is on this study, they might be excluded from other studies. This coordination of all this data is is a key requirement of running large-scale clinical trials, especially in rarer diseases. On the next animations, you'll see the sort of closing the loop of how this cycle works. And each independent clinical trial could be sponsored by many different organizations. So there are German research centers who get grants to run a clinical trial. There are, the French have got clinical trials running. There's lots and lots of activity around this, building a central model where lots of data allows collaboration to happen. And if you go to the next slide, you'll see the kind of things that the doctors are doing with this data once they collect it is that typically they'll produce guidelines. On the next slide, you'll see there's a whole range of publications that they will have. And this is just the most recent ones. So they publish in the very top journals, the New England Journal of Medicine, the Nature, the Lancet, etc. The most recent publication was being able to diagnose a patient and the type of cancer they have just from a urine sample. So again, this is kind of at the edge of what researchers are trying to do in managing cancer. So that's an example of a single project, which is based upon a centralized, let's build a registry and everyone logs in to create information on patients. It doesn't talk to the hospital systems at all. It's completely independent. As I mentioned, sometimes that model doesn't work. Another example is a push-based system where data from the hospitals is being pushed to a central registry. So on the next slide, I'll tell you through one example of this, which is called the Australasian Diabetes Data Network. And so this is just the example of the hospitals themselves are pushing data out now. It's not a clinician logging into a system to create a patient. It's actually hospitals are pushing this data out. It gets processed, cleaned, checked. Feedback is given to the hospitals about the quality of their data. And then again, once it reaches a certain level, they will accept the data and the researchers can work with the data. So an example of this, as I say, is the Australasian Diabetes Data Network on the next slide. And this project was funded by the Juvenile Diabetes Research Foundation. It's been going for 9 years now. And it's about patients with type 1 diabetes. The original focus was on pediatrics, so children with type 1 diabetes. But we've since grown to become a pediatric and adult, as well as including now New Zealand. But the point of this is that it's not just a separate system, it's actually integrating data from hospital sites. And every hospital has its own infrastructure, its own needs, its own demands, its own schemas, its own Oracle or Excel, or however they're managing their data. They have completely heterogeneous systems. So my job is to pull in this data to a single uniform platform. Just to give you an idea of the scope of the collaboration, you'll see this is on the next slide, we have a map of Australasia with multiple pediatric and adult sites that are involved across the country. These sites are continually growing. We're expecting another 20 or 30 sites because we're just getting another grant from the JDRF to extend the work. Both from the major centres, which is where our focus has been right now, the main hospitals in Melbourne and Sydney and Perth, etc. But we're now going to the less populated sites, like rural hospitals, for example, which may not have 1,000 patients every day or every year, etc. It might be a few hundred. But still, this is kind of the focus of our work. On the next slide, in terms of how we do it, there is a central database which my team develop and manage. There are multiple different systems that are existing in hospitals. So there's technologies that they use. One of them is called DPMS. There's another called EPMS. There's some sites have got ad hoc systems based upon access databases and spreadsheets. For the adult centers, it's a similar situation, but we're using some linkage technology called BioGrid, which is a way to connect data from different sites in a secure, privacy-preserving manner, where all the identifying data on the patients is replaced by a unique ID, which is generated, called a universal subject identifier. And based on that, then we can start tracking these patients as they move through the system. And so when they first come to a hospital as a child and they're taking certain treatments, how are they progressing as an adult? On the next slide, you'll see some of the statistics of these patients. So we have 17,000 patients in the system. Again, the number is, Australia's got a population of 25 million, give or take. So it's not like it's not as common as the cold, but it's certainly a lot more information that's being collected on these patients. We have 229,000 visits. Our focus was initially pediatric, but we've also now, in the last couple of years, engaged with the adult centers as well. So we have a lot of data now on patients and how they're being treated. And on the next slide, you'll see what we can do with this. So we can see which centers have the most patients. And so each center will have pediatric patients, adult patients. They might have patients with type 1 diabetes, with type 2 diabetes, etc. Based on that, we offer tools for them. So one of the tools we offer is that as the data is coming in, it generates reports. So we can say you have a 300-kilogram baby, or you have a man that's pregnant, or you have someone whose values here can not possibly be correct. So we generate reports for each site based upon the data that we're provided with. And once the data is being cleaned at source, it's uploaded again or fed into the system. And once it reaches a certain level of completeness and validity based upon our data model, we can then use that in the system to do all kinds of things like benchmarking. It's one of the interesting, just as an aside, aspects of this project is that we have a completeness requirement. So if certain data is not being provided, and it should be provided, we don't accept the data. And we only get paid by our funders if we fully meet the number of patients and the quality of the data. So it's an interesting manifestation of building a registry populated with live data to make sure that the data is as good as it can be. You basically only pay for it if you only get our funding if we meet the criteria, which does give you higher data quality. The kind of things we can do with this is just a couple of examples. So you sort of see the distribution of the ages between the different centers. The top left is adults and how many people with type 1 diabetes have their age distribution. The bottom left is for the pediatrics, and you can sort of see there are way more 12 to 18-year-olds that have diabetes than others. The top right is now moving into what the doctors are actually interested in. So this is looking at the HbA1c, which is the blood sugar content, and how many the national guideline for regulating yourself is supposed to be 7.5 or below for your HbA1c. And as you can see, in not many sites in green, as shown here, are actually achieving that. So sites can then start looking at implementing policies to say, how do we, is it, how can we improve this? On the bottom right is how the patients themselves are being treated. So this could be through different types of insulin. It can be through injections. We're doing work now looking at continuous glucose monitoring. There's a whole range of analyses looking at, how are patients being treated who have type 1 diabetes, and which of these kind of treatments works the best for them to achieve the best outcome for the patient. So that was another example where we're getting data pushed into the system. A third example is where where we build a system that directly talks to databases over the internet. And that's not an uncommon model as well. It's not so relevant for a lot of the medical world because they are obviously hidden behind firewalls and there's privacy and security, but there's still a lot of work that we work on where we can programmatically access data online. One of the projects I'm involved in that space has been going since 2010 called Orem. The Orem Project is based upon federated access to distributed data. So we have a platform here where anyone in Australia who's an academic can log in. So we're using single sign-on through the Australian Access Federation, which is using technology called Shibboleth to authenticate and then provide access to very heterogeneous, diverse data across Australia. The focus is around data in cities. So for example, if you wanted to know about whether the Chinese people live in Melbourne, you might get that data from the Australian Bureau of Statistics. If you wanted to know how much crime is happening in Melbourne, you might get that from the Victorian Police. If you want to know the average price of a house in Melbourne, you might get that from another agency. So there are lots and lots of agencies and government bodies that have this data at the local level, at the state level, and at the federal level. And so this system, it's a very large project. It's probably had about $60 million of funding since it started, is about providing federated access to all that data with a whole range of tools for analyzing, comparing, and doing things with the data. So for example, increasing crime, how does that equate with the amount of alcohol consumed, or the amount of people with a certain condition, like obesity, for argument's sake, is how much of that is impacted by, there's not as many parks to play in anymore, for example. And so the system itself has a lot of data, and on the animation, you'll see that we have interface to 149 organizations right now. That's major agencies across Australasia, where we are building systems that talk to their systems to pull in their data. So there's just under 6,000 data sets now, these are not just any data sets, this is definitive data. So this is the official statistics of information in the cities. And as one example of applying this, I'll just show you on the next slide. I've just produced a visualization. So this is looking at data, which is to do with cancer patients. So in this case, it's lung cancer. So I work in many different disciplines. So this was one where I was working with the Victoria Lung Cancer Registrar, and they provided access to their data. And this is what the doctors are dealing with. This is the number of patients who have certain types of lung cancer. What they don't know about is any causal factors. So do they smoke? Do they live next to a motorway? Do they live next to an oil refinery, which is polluting, et cetera, et cetera? So in the background map here, which is called the Coropleth Map, you can sort of see we have bright pink and pale pink, and then no, that's literally just looking at the distribution of cancer patients around Melbourne. The centroids, or the circles that you see in the colors, are factories that pollute, and they pollute to a certain level. So if you're running an oil refinery or a steel works, what have you, you are allowed to pollute within a certain threshold. If you exceed that threshold, you get fined. That's kind of generally the model. And so we can take them data layers and then connect it with the cancer patient data. What you don't see on here, but we have as well, is how many cars are on the road network. If you zoomed right in, you would see the number of vehicles that were traveling, going through these areas, and how many trucks and how many cars and how many diesel, etc. So we now building layers of pictures of data that are informing the distribution of cancer patients. So it's not just you were unlucky to live in that area. It might be there's a local environmental context around that. Very rapidly, because I'm running out of time, there are two other models which I'll briefly talk about. One of them is this notion of a pull-based query. So we've worked with organizations that have unit level data, and they don't want that data to be released for obvious private reasons. So for one example here is Vic Health. They run a survey. This is a Department of Health in Victoria. There's 25,000 people each year that are interviewed about, do you drink, do you smoke, when was the last time you went to the cinema? And based on this information, they aggregate it and they tell a picture of the lifestyle and the health of people in Victoria. So we had to build a system that could interrogate the unit level data and release aggregate results. And so that's another one where they have to pull in queries, run some analysis, and then release aggregate results. So for example, the people who drink lots of alcohol live close to a place where you can buy alcohol. So we know the places you can buy alcohol, but we don't know where these people live. By pulling in the location of the bottle shops, as they call them, the bars, we can connect that with the location of the people and who spends more on alcohol. And that's kind of where the kind of a typical kind of scenario. The final one was a dependent security under push model. So this will be the ideal. There's a standard set of technologies where I can run a query. It gets intercepted at a firewall and by a service. In security terms, it might be a PDP, a policy decision point, and a policy enforcement point, which says, this is Rich, he's trying to access this database. Do we allow or don't we allow him? I've not yet ever had to deal with that scenario. No organization I work with is savvy enough yet to provide those kinds of services where it's access control, where it's based upon who you are, what you're trying to do. They basically just don't deal with that. The best you can generally get is they can check your IP address and they lock it down to a single, IP, allows incoming connections, but that's limits greatly the capabilities. So just in summary, on the work as a whole, I've presented a range of different ways of sharing health data. There's no one recipe, there's no one solution that fits all purposes. And again, I continually have to reinvent solutions to meet the problems I face with. And a lot of the time, these problems are not always well defined. Even just sharing data across Australia, different states like Victoria and New South Wales and Queensland have different rules and regulations about what can and can't be shared. So, and they continually evolve. There's not like one solution fits everywhere. One of the main things I've learned is that it takes time to build a relationship, to build the trust, to work with these organizations. And that's just something which it's very hard to build up, but it's very easy to lose. And if bad things happen with that data, then it would be disastrous for them and I guess for me. So we're very we try to be as risk averse as possible. The only final point I'll make is that this is very much a technology sort of perspective. One of the real challenges, and I don't see any solution to this around the corner, is the legal aspects and dealing with lawyers and contracts and things of that nature. So a lot of the work I've described here is once you get the green light to do it, it's very challenging to create those green lights. The legal aspects of data sharing is very much in the lawyer's land, and the information governance and the policies, etc. This is very much process heavy, and quite rightly so. I mean, if it was all easy, then bad things would happen with the data. But there has to be a more streamlined process for doing this. And that was the end of my talk. Thanks very much.